Welcome to the Explainer. Have you ever stopped to actually think about what happens the exact moment you click a link or hit send on an email? It feels instantaneous, right? But in those literal milliseconds, there's a massive, incredibly complex, and completely invisible negotiation taking place between computers all across the globe. Today, we're going to demystify that invisible world. We're exploring exactly how your data travels across the internet, focusing specifically on the foundational mechanics of the transport and application layers.
Here's our roadmap for today's Explainer. We're taking a bottom-up journey. We'll start with the transport layer, see how connections are established, and compare TCP and UDP. Then, we're moving up to the application layer, checking out the client-server model. And finally, we'll wrap it all up with the everyday protocols that make things like email actually function.
All right, Section 1, the transport layer explained. You can basically think of this layer as the internet's master shipping department. So before we get too deep into the weeds, let's frame the core problem. Imagine you've got host 1 and host 2. They're on completely different networks, maybe even different continents. They obviously aren't physically connected with a cable. So how do we guarantee that a message from an application on host 1 securely and accurately reaches an application on host 2? Well, to solve this, the transport layer creates what we call a logical communication path between the application processes running on these different hosts. Even though the data is physically bouncing through routers and cables way down in the lower network layers, these applications act as if they have a direct, dedicated pipe between them. They just pass units of data called TPDUs, or Transport Protocol Data Units, back and forth. The absolute crucial takeaway here is the ultimate goal of this layer, providing efficient, reliable, and cost-effective data transmission. Think of a high-end courier service. They don't just throw your package on a truck and hope for the best, right? The transport layer tracks, manages, and guarantees that your data arrives exactly as intended. It uses specific addresses called ports to make sure the data goes to the exact right app, not just the right machine. Moving into Section 2, establishing the connection. Because before our courier can start moving those packages, these endpoints actually need to say hello.
Establishing a connection over an unpredictable network is notoriously tricky. Packets get delayed, they get lost, they get duplicated. Imagine if a delayed, duplicate connection request suddenly appears from an old, long-dead session. That's a huge problem. We need a way to ensure host 2 doesn't accidentally open a connection nobody actually wants. And that's where a brilliant solution from way back in 1975 comes in, the three-way handshake. Let's walk through how this three-way handshake solves the problem. Step 1. Host 1 sends a connection request with a specific sequence number. Let's just call it X. Step 2. Host 2 gets it and replies with an acknowledgement of X. But crucially, it also announces its own initial sequence number, Y. Step 3. Host 1 receives that and sends a final acknowledgement of Y. Why is this so clever? Because if host 2 gets an old ghost request, it will reply proposing its Y sequence. When host 1 gets that, it realizes it never initiated this connection, rejects it immediately, and disaster is totally averted. And just a quick aside here, saying goodbye securely is just as critical. The transport layer handles connection releases too. You can have an asymmetric release where one side hangs up and it's over, kind of like a phone call, or a symmetric release where each side of the two-way connection closes separately. That ensures absolutely no data gets cut off while it's still in transit. Section 3. TCP versus UDP. Now that we've got our connections made, let's look at the two main delivery trucks the transport layer uses.
Out on the internet, you basically have two choices. First is TCP, or Transmission Control Protocol. This is your certified mail. It's connection-oriented, it's highly reliable, and it flat-out guarantees delivery. If a packet gets lost, TCP will retransmit it. Then we have UDP, the User Datagram Protocol. Think of UDP as a postcard. It's connectionless, no handshaking dialogues, it just fires data off as fast as humanly possible with absolutely no guarantee of delivery, ordering, or duplicate protection. TCP is the absolute workhorse of the internet, and it ensures that perfect reliability through some pretty ingenious mechanisms. It uses a sliding window protocol to make sure a super-fast sender doesn't drown a slow receiver, and checksums to catch any corrupted data. But what happens when the entire network gets congested and starts choking? That is where TCP's congestion avoidance shines. Advanced networks use incredible algorithms to handle this. Take DECbit, for instance. With DECbit, routers that are experiencing a massive traffic jam will literally set a specific bit in the data packet. It's like slapping a tiny slow down sticky note on the packet so the hosts know to ease off. Or networks might use RED, random early detection. Instead of waiting for a router's queue to completely overflow and drop everything, the RED algorithm proactively drops a few random packets early. Because TCP is designed to notice those dropped certified packages, it automatically throttles its sending speed, which avoids a massive network crash. UDP, on the other hand, it ignores the whole shebang. No flow control, no congestion avoidance, just pure, risky speed. Perfect for live video where a dropped frame is better than a buffering screen, but terrible for downloading a file.
All right, Section 4, the application layer. We are officially leaving the shipping department and arriving at the storefront where the actual internet services live.
If you look at the grand scheme of the TCP/IP hierarchy, the application layer sits right at the very top. It rests directly on those TCP and UDP transport protocols we were just geeking out about, acting as the ultimate destination for your data.
Our sources hit the nail on the head with this quote. The application layer is closest to the end user. When you open up your web browser, or use FTP, or check your email, you are interacting directly with application layer protocols. This layer is the literal interface between your software and the underlying network.
Moving to Section 5, the client-server paradigm. Let's see how these applications actually organize themselves to get work done.
The internet relies incredibly heavily on the client-server paradigm. And it's exactly what it sounds like, a structure that divides up tasks. On one hand, you have the server, the resource provider. It just runs continuously, sitting there waiting for someone to ask it for something. On the other hand, you have the client. That's your laptop or smartphone, the service requester. Clients initiate the communication to get the data.
Now, it's definitely worth contrasting this with the other major setup, peer-to-peer, or P2P. In traditional client-server, you need a beefy, always-on computer acting as the server, which concentrates all the cost and processing power in one place. But in a P2P network, think BitTorrent, you don't have that expensive central server. The responsibility is shared equally among everyday users or peers. It's highly scalable, super cost-effective, though admittedly it can be a bit harder to secure. Finally, Section 6, Everyday Network Protocols. Let's take all of this invisible architecture and see how it supports something you probably do every single day.
Let's trace the journey of an email. When user 1 shoots an email over to user 2, it is not just one magic action. It requires multiple application layer protocols tag-teaming seamlessly over those TCP connections we talked about.
Here's how the handoff works. Step 1, your email app uses SMTP, the Simple Mail Transfer Protocol, to push the message to your provider's mail server. Step 2, that server acts as a message transfer agent, talking to other servers across the internet, again using SMTP, to route the message to the recipient server. But here's the catch. SMTP is only for pushing messages. When the recipient wants to actually read that email, they can't use SMTP. Step 3. Their software uses a message access agent protocol, usually POP3 or IMAP. These are pull protocols. They authenticate the user and literally pull the messages down from the server to the device.
Which brings us to the end of our explainer today. I want you to just think about everything we covered. The logical transport paths, the exact sequence numbers, the TCP error corrections, congestion algorithms like DECbit and RED, the client-server requests. As you're sitting there right now watching this, your device is flawlessly executing thousands of these operations every single second. Seriously, how many invisible three-way handshakes do you think your device just performed just to stream this explainer? The internet isn't magic, folks. It's an unbelievable symphony of structured negotiation. Thanks for learning with me today, and keep questioning the tech around you.